Greetings! Welcome back to the Old Ways Rising Farm YouTube channel for the third installment in our little breeding and genetics overview. Now, this is genetics as they apply to breeding programs that you might experience as a homesteader. This is not a full deep dive into all of the nuance and technology related to the field of genetics. Okay? The structure of this video series is such that the first video was a lot of basic terminology. The second video was an extension of that, where we went over Mendelian genetics, heritability, inbreeding depression, outbreeding depression, minimum population sizes, 5,500 rules, all of that sort of stuff, with both understanding how genes work and understanding population genetics and how that relates to your farm. This third video is where the rubber meets the road, and we're going to talk about specific breeding patterns and how they depend on that knowledge that has already been built. So, if this is the first of the series that you have come into the channel on, if you find yourself feeling lost, that's because I am relying on information in those previous two videos. Okay? I will pop a link. YouTube won't let me put multiple links at the top of the screen for the first two. I will make sure that I pop a link to the playlist that contains all of this information down in the video description below. Okay? So if you feel yourself getting lost, pause it, go look at those earlier videos, and then come back and you'll be caught up nice and straight. Okay? So, what we are going to talk about in here are three broad categories of breeding program styles. Okay? The most intensive is line breeding. Okay? The least intensive is mob or random breeding. Both of those words have some problems, but anyway, they're the commonly used words for the method. And then intermediate is family or clan breeding. Okay? There's a lot of nuance, there is a lot of variation within all of those schemes, and a lot of different things that can be done. We're not going to cover the totality of it. This is an overview video series, right? There isn't time to cover the totality of it. But I do hope to explain to you and help you to understand what each of them does well and where each of them fails. And I said it that way for a reason. Each of them does something well. Each of them does something poorly. Okay? So nuance is everything in this conversation. Right? There is a certain group of people that have decided, well, ... insert their favorite method is the only way to breed. Or ... insert their least favorite method is evil and should never even be thought about. If you're either of those people and you're going to get grumpy with me saying something good and bad about all of these methods, just go. You're not going to enjoy this video. Go watch somebody who's going to support your preconceived notions. I'm not that somebody. If you want to understand the nuances which make each of these beneficial for something and deleterious for something else at the same time, keep watching. And at the end of this, you'll understand what they do. And from that understanding, you can pick and choose how you want to apply them in your own breeding programs. So, if that's you, keep watching and we'll dig in. Just a couple more very quick terms. Okay? Purebred and hybrid. Purebred references something being homozygous for a specified trait. Okay? Hybrid means something that's heterozygous for that specified trait. Now, the specified trait could be literally anything. That's defined by your breeding goals. If we're looking at a trait, it means it's of sufficient interest to you as the breeder to have identified it and you're digging into trying to manipulate that trait in some way. Okay? But this could be any trait. This could be related to disease resistance. This could be related to, hair, fur, feather color. This could be related to weight gain. This could be related to anything. Okay? Now, purebred just means homozygous. Saying something is purebred, you're saying it's homozygous for whatever you're talking about. Okay? there are some people who will say purebred means that you have been accepted into some certain breed club. Baloney. That is not what it means. That ain't what we're talking about here when we're talking about something being purebred, right? If your line of sheep is purebred for white wool, that means they are homozygous and all sheep will have white wool. Okay? If you occasionally have black wool sheep coming out of your herd, that means your herd is not purebred, it is hybrid for that characteristic. That's all they mean. Okay? Now, both of these can be an advantage or a disadvantage. When we're talking about production traits, usually you want them purebred. Okay? When you are talking about disease resistance, usually you want things heterozygous or hybrid. Okay? Remember, we talked about this when in the last video when we talked about inbreeding depression and how it develops. The immune system, in order to be able to produce a large number of diversely formed antibodies, which can attack a large number of diverse pathogens, you need a hybrid condition at the loci which make antibodies, right? The long chain and short chain antibodies, proteins within an antibody, you have multiple genetic loci for both of those. If they're all the same, you have a reduced number of diseases you can fight. If they're all different, you have an expanded number of diseases you can fight. So as you build purebred in one area, you can become purebred in places where you need to be heterozygous. This is why nuance is everything, and there's always a give and take between fixing a trait that you want and not fixing problematic characteristics. And when I say that, like the immune system will collapse in conditions where it's overly purebred, that's not saying that any one of those genes is bad or wrong. It just means they're all the same, so you don't have as much to start with. Okay? It's like a hardware store that sells only hammers. Well, sure, you can find the perfect hammer for any nail you want to hit, but heaven help you if you need a screwdriver, right? Same thing. And that's where we get in trouble with some of the methods which really push toward purebred production characteristics rapidly, also push toward purebred immune characteristics rapidly. So it's good for one, bad for the other. There's always this give and take. Okay? Now, last really quick one, and this is going to be real important when we talk about line breeding, is a test cross. Remember your dominant recessive. If you have a true dominant recessive characteristic, whenever the dominant gene is present, the recessive gene is invisible. Okay? So I just made up a loci. We have these big F's here. We've got them little f's there. Okay? Dominant and recessive. I'm not saying that recessive is bad. I'm just saying it's not dominant. Okay? Now, if you have a population where everybody is heterozygous, hybrid for this characteristic, for this trait, they will all look like they are dominant. But you don't yet know if they're purebred. The test cross tells you if they're purebred. Okay? So here's how you do the test cross. You have to establish a line of, and we'll talk more about this in a second, you have to establish a line of that organism which is purebred recessive. Okay? If you have an individual and you don't know if it's purebred or hybrid, okay, you cross it to purebred recessive. If it's purebred dominant, all of the offspring will show the dominant characteristic. Okay? Hopefully that's what you want, right? Hopefully if you're having to do this, you're looking for that dominant characteristic. Okay? Mm-hmm. Now, if you have a hybrid individual, when you do this test cross, half of them will show the dominant characteristic. Half will be purebred recessive again, and will show this unwanted or negative, because if you're testing for it, it's something that you're trying to get rid of, right? So based on your breeding goals, you have defined these little effers as something you don't want, okay? Now, that doesn't mean they're bad. It just means it's something you don't want, right? You're trying to test for it. So you breed for a purebred little f population, you cross it to your unknown individual, and you see if you got any of these little buggers in there. And this reveals that. This is very easy to do if you're doing like hamsters, rabbits, or chickens. Because, you know, if this is a hen and this is a rooster, you can just collect 2 or 3 dozen eggs from that hen and you'll get a good sampling. This is very hard and expensive to do with cows and horses. Because let's say that this is the bull or the stallion, okay? And we have a population of homozygous recessive females. You need to breed this stallion to fully a dozen females.
Oh my goodness.
Okay, yeah, oh my goodness. Right, and now we're talking hundreds of thousands, if not more, of dollars in livestock. And since all of these are culls from the program, and all of the offspring of this in general are culls from the program because we just force them to be hybrid. Right? So this is very prohibitive in things like, you know, cows and horses. And therefore, it's typically avoided except in, you know, like academic and university-driven experimental programs. Okay, farmers don't usually do this. Very easy to do with chickens, very cheap to do with chickens. You know, most of your chickens are going to end up soup anyway, so no problems. But when we start talking about cows and horses, this gets real expensive. And further, when we start talking cats and dogs and animals that, you know, people love as part of their families, this gets ethically dubious, right? Do you want to breed an entire population of dogs with hip dysplasia in order to test for the existence of hip dysplasia? That's what we're talking about with a test cross, okay? That's very ethically dubious, right? But we're going to talk about this as it relates to executing these other methods. So I wanted to put it up here on the board right to begin with. Now, let's start and dig into line breeding. Line breeding. This is where we're going to start. It is the most intensive of all of these methods, and it is the most controversial. Right? This is one of those where you will have people that say the only way to ever breed livestock is line breeding, and you will have people that say you should never ever line breed under any circumstances. Okay? I'm going to explain what it is. I think it does have a use, and I think it is often misused. Right? So I'm a little bit in the middle, which means both sides are going to want to run me over. But anyway, moving on. So the place where I think this has a lot of use comes from the fact that it is the fastest way to fix a purebred condition in a line of livestock or plants or anything that you're working with, right? Now, a line is a population that has been line bred, right? So the offspring of a line breeding program is a line, right? Fixing a trait in that line means that the entirety of that population is purebred for the trait that you're going to work on. Now, here's the first point where we get into use and misuse of the technique. Okay? It is a really good way to rapidly fix a single trait that you want to introduce into a larger population. Okay? So let's say you're breeding chickens. We're just going to use chickens as our example for this. There's historical reasons for that. You'll see here in a minute. But let's say you're breeding Rhode Island Reds, and you just get just a spectacular Rhode Island Red for some specified reason. Maybe it has a different than average comb type and you want to keep that, or maybe it threw a rare coloration and you want to keep that, or something was notable. Okay? Well, if you have 100 other chickens and you just take this one chicken and throw it back into the main flock in a mob breeding program, that single trait is just going to be diluted out so much that you're never going to see it for another 30, 40 generations until you have another chance, until it just pops up by chance again. Okay? So we want to make more of that chicken so that it will be a larger percentage of the overall mob and, or clan mating system, whatever else you're doing. And you're doing this as part of a larger program. Okay? That's where it really, really works and where these techniques are really, really valuable. Okay? Where it doesn't work is when you're trying to use line breeding to reproduce some external arbitrary breed standard in its entirety. Okay? If you are trying to line breed to fix 30 traits simultaneously, I can absolutely guarantee you're going to accumulate problems faster than results. Don't do it. It is not the right system for managing the totality of your breeding program. It is the right system to say, oh, this cool thing happened and I want more of that cool thing, so I'm going to make a whole bunch of it by brute force, but then revert to another more holistic program. Okay? That's where it's useful. That's where it's really useful. So, what is it? This is coming from a historical process called the Cocker's mating system. This is why I'm using chickens as an example. Okay? Now, the Cockers were farmers that were involved in breeding fighting chickens, fighting cocks. Okay? Now, I am absolutely not advocating for this. I think it's horrendous and it's horrible, but it is the history which contributed to the development of line breeding as a practice. So since it is a historical thing that has happened, we need to talk about it in order to understand this technique and where it comes from. Okay? Purely history. Please don't, attack me in the comment section about how bad cockfighting is. I know how bad cockfighting is. It's horrible. It's evil. It should never be done. I agree. But it's the history of this method. So we're acknowledging historical fact. And it's very old, right? This goes way back into medieval time, using line breeding in the Cocker system. Okay? So the trait that the Cockers were selecting for was increased testosterone production. That's why fighting cocks are ornery, because they have such accelerated production rates of testosterone. It's like, people who are, abusing illegal performance-enhancing molecules. They get rage problems. Well, you're breeding that trait into the fighting birds, right? So you're breeding them to live in a constant state of roid rage, so to speak, okay? Again, this is a horrible thing to do. Don't do it. But that's the trait that they were looking at when they developed this system. So here's what you do. Let's say that you have, and we'll come back to this in a second, but let's dial it out to a less vile concept of animal breeding and say, go back to your breeding egg-laying chickens, and you have one that just has this marvelous egg or this marvelous color pattern or something. Okay, let's say, and let's say this popped up in one of your females, one of your hens. Okay, so you want this feather color or this egg color or this egg size or whatever it is. You want this to become a dominant component and a defining component of your greater flock, but you only have one. So you're going to take her and you're going to do a single pair mating with another male from your flock. Okay, you're going to get offspring. These two original parents are the P1 generation, the offspring are the F1 generation. Okay? So these F1 males, we're going to look at the male to female direction. You could also do female to male if it's the rooster that you identified the trait in. It would be the mirror image of what I drew over here. I don't want you to think it has to be one or the other, right? Which is why I drew some arrows over there. But this F1 generation, the first progeny, are 1/2 genetic components from your original hen. Okay? So in the second generation, we're going to take one of these roosters and again pair mate with this hen. Whichever rooster seems to be the most likely to help you fix this trait that you're after. Okay? That's going to give you an F2 generation. Ignore the red for now. We're going to come back to that in a minute. That's going to give you the F2 generation. The F2 is 3/4 genetic component from the original hen. Okay? So we're going to take a male from here, breed it again back to the original hen, and F3 is going to be 7/8 the original hen. If you do it again, F4 will be 15/16 the original hen. Okay? Now, by the time you get to F4 and F5, we're starting to build problems. Remember, problems from line breeding are not just the prevalence of a deleterious gene. They are the absence of heterozygosity in immune function and other similarly heterozygous condition-dependent physiological characteristics. Okay? So losing heterozygosity, becoming more purebred, is in and of itself a fundamental problem. That's what you have to understand. You cannot cull your way out of that fact. Too much homozygosity will collapse the population. Period. Not because any of those genes are bad. They're all good. It's the simple fact that they're all the same. Okay? So this is where we come back to the Cocker system. These cockfight people would have 2 or 3 lines going at a time on their farm, but they were participating in large guilds or clubs, which might have 100 members, right? So as we get out to F3 and F4, we're basically cloning the original female. This is why this sort of breeding is done far more with animals than with plants. It is done with plants. We will talk about that later. But it's done more with animals because most plants you could just clone by rooting cuttings or grafting your apple tree. You don't need to do this. If you plant apple seeds and you get this wonderful apple, you don't need to go to this sort of extreme manipulation to get clones of it. You just graft more, right? Or air layer, or root cuttings, or one of these other plant propagation techniques that we've talked about before on the channel. But with animals, you can't do that. Okay? With annuals, you can't do that either. That's why we do this kind of breeding with corn, right? So these F4 and F5 are basically clones of the female, but they're accumulating these problems. So let's say every cocker in the Cockers Guild has 3 lines. Well, functionally, no matter how many birds they've bred, they have an effective population of 3. Because each line is functionally a clone of the original male or female that started it. Right? So they each have 3 birds. But if you have a Cockers Guild with 100 cockers in it, they each have 3 lines, you now have an overall interacting population of 300 because once they get out to F5, they trade stock. Okay? And because the primary source of inbreeding depression, of unavoidable inbreeding depression, I'll say, is that reduction in heterozygosity, it can be reversed with 1 outcross in 1 generation. Right? So, yes, each of these lines is severely restricted and not long-term viable. But because the Cockers Guild is a larger metapopulation, it's still okay. And this system persisted from just after late Roman and just after Roman times, clear through to the banning of cockfights. Okay? So it was a viable way to breed chickens for horrible reasons, but to breed chickens in general for a very long period of time. Okay? Because they were operating as community. Now, this falls apart if you're not operating as community. If you're the only one breeding a particular animal and you don't have people to trade stock with easily every few generations, you will fall flat on your face if you try to do this, okay, and maintain it permanently in this condition. This is why I say where I think line breeding is most useful to a homestead scale breeder is when you have these cases where you say, oh, this is an awesome, amazing example of an individual. I will line breed it just until, not all the way out to F5, but just to F2 or F3, so that I concentrate those genes, and then I'll take the best 5, 10, 15 individuals, depending on the size of the larger herd or flock you're dealing with, reintroduce them to an otherwise genetically diverse population, right? You've taken this gene, you functionally cloned it into a large number of animals, you put it back in, so now it has a high chance of becoming a defining characteristic of your stock. And you can use selection and culling to guide that further without getting to these extremes of inbreeding depression. Okay? That's where I think it has a role. And that is the traditional role of this sort of thing, right? The Cocker system is called that because it's such an exception to the way livestock is normally bred. Now, there's a second wrinkle to this, and that is you have to understand an idea called genetic burden, right? Everybody, whether you're human, animal, a chicken, a plant, a bird in the sky, right? It doesn't matter. Every living organism has a genetic burden, okay? Your genetic burden is the suite of deleterious traits that are part of your genome. The majority of them are hidden in the homozygous condition because most deleterious genes are recessive. Okay? Not all. Huntington's chorea is an exception, like a very famous exception to that. That's a dominant lethal gene. Okay? But the overwhelming majority of lethal genes, bad genes, genes that lead away from, you or another organism having a healthy, productive life, tend to be recessive. Because if they are dominant, they will lead to either an unsuccessful pregnancy or hatching, depending on whether we're talking like mammal or bird, or even if they do have a successful pregnancy or hatching, they will be selected against over evolutionary time, right? Either due to, decreased frequency of mating, not living to sexual maturity, or, in some other way being removed from the gene pool, right? If you can't run as fast, you're not going to have as many offspring on the Serengeti, okay? Right, so bad genes that are dominant tend to be removed very, very rapidly from the gene pool. The reason Huntington's is the exception which proves the rule, the reason that has persisted in the human genome is because it doesn't kick in until the person is 30 or 40. And if you look at, historically, when the life expectancy of the average person was 40 years, it was really just thought of as more, a symptom of old age. Okay? So because of that, since people have already done the majority of their reproduction by the time Huntington's kicks in, evolution was not able to remove it from our gene pool. But you still, yes, you're watching this, you're alive, you're a human, you have a genetic burden. So does every animal on your farm. Okay? Now, as we move toward a more and more homozygous condition, that genetic burden is going to crop up and show itself. So this is the second component to correct line breeding. I'm just sticking with my, big F and little f gene here from the previous board, right? Let's say in the F2 generation, these little f's crop up, and this one shows that negative trait. Doesn't have to be a lethal gene. It could just be like the wrong color feather. I don't care what it is. It's something that doesn't belong in your breeding program. Okay? This could be a bad coloration. This could be hip dysplasia, or this could be producing a third leg in chickens, right? This is something that you don't want. Okay? Now, that means that this trait is carried by your original female. Okay? So, all of her offspring have a 50% chance of containing it. Okay? We want to remove this from the population. We're going to this extreme, we're line breeding, we want to remove this negative trait. Now, here's where there's a big lie told about line breeding. Right? You will have advocates of the system who say, as long as you cull heavily and remove all of these that show the trait, you will eventually remove it from the population. That is bogus, because the fact that it's here means this original mom's a carrier. Okay? So you're not eliminating it, you're guaranteeing its continued existence. Okay? So what we do is we're going to take this offspring and we're going to make sure this is, okay, that's a female here, right? So we're going to make sure that this hen is set aside and is nurtured. This is if this is something which makes it difficult to nurture, she may need more husbandry than the rest. We're going to breed her to one of her brothers. Okay, we're going to stay within this generation, not going back to the original mom, right? Obviously, that would not work, right? So we're going to take her, we're going to breed her to one of her brothers. Now, that sibling cross, in all likelihood, you know, these are both carriers. We know that all of their offspring will at least be carriers. Probably about half will show. Assuming he's a carrier, half of these offspring will show that negative trait. We're going to build a small but viable population in which we have fixed a trait we don't want. Okay? You might need to go to an F2 with this. You might get it in the F1 from this mating. Okay? That is a test cross line. Now, when we get out here to F3, F4, F5, depending on how far we're going to go with this pattern, before any of these offspring are reintroduced to the larger herd or traded with other farmers, okay, or put into a clan mating program, before we do anything else with these, we're going to take this test cross line and we're going to test cross all of them. And they only get from the line breeding program back into the main flock once that aspect of their genetic burden has been removed. But you can only remove it with a test cross. You cannot remove it by simple selection and culling. Okay? Because recessive traits are definitionally hidden in the heterozygous condition, of course. Okay? Now, this is why I put this up. Never ever line breed without also doing a test cross. Okay? As you line breed, you're going to find these little effers. Okay? You're going to find them. When you find them, you fix them in a line. You use that line in which you fix them to test cross the final offspring of this program. And after F4 or F5, you test cross all of the individuals which pass the test cross, go back into the herd. Okay? Or cross with another line or taken somewhere else, because this is where you start to lose your viability. Okay? And remember, removing these does not make these viable. These are not viable because they don't have enough heterozygosity in their immune system. Okay? And other locations. Immune system is my main example. It's not the only place where you have problems coming from low heterozygosity. Okay? So, ignoring this rule is a huge problem in modern animal husbandry, especially. Right? Ignoring this rule is why we have so many purebred dogs with hip dysplasia. Okay? Because nobody wants to do this with dogs. This is socially acceptable to do with chickens and inexpensive to do with chickens. Right? But it's not socially acceptable to do with dogs, and it's not economically viable to do with cattle and horses. Okay? So this gets ignored. Any line which has been produced by line breeding and has not had a test cross system done to remove the revealed genetic burden should be entirely culled. Okay? You cannot take that, reintroduce it to your herd, and not have problems. Okay? You must do this. If you are not willing to do this, you are not willing to line breed properly. Okay? Now, just because you say, okay, I'm not willing to do this, I'm not going to line breed, the sad part is this has been done wrong so many times, it's almost impossible to get livestock where this hasn't been done and done wrong, right? So almost no matter what you're working with, you're working with stock which had this done wrong, okay? And that is where we get into some of these other breeding patterns and other ways of dealing with this. Some of those we're going to talk about here in this video. Others we'll talk about when we get to the outcrossing video. But up next, we have a slightly less intensive, but still very directed method called family and clan mating. Moving away from the most intensive method and honestly hardest to execute properly, right? Line breeding is very difficult to get right and very easy to get wrong. Very powerful when you get it right, but very easy to get wrong. This is still an intensive method, but it's not as intensive, okay? We're talking about family mating, clan mating, or spiral mating. These are the three most common names that you'll hear for this. It's not just a one-size-fits-all method. There's subtlety and nuance and different ways of applying it, yes. But we're going to kind of talk about a big overall view. And these words tend to all reference the same general idea most of the time. Okay. Yes, I know word use can vary, but most of the time we're doing this of some form, and the variations will come more from differences in starting material, starting point, and breeding objectives from one farm to the next, more than from an understanding of what's at play when we set up this sort of mating system. Okay. So, what we are doing here is we are taking a population and we are splitting it into families. Okay. Now, a lot of people, there's different ways you can use it. One way is you say, okay, what I have is already great. I want to grow my herd or flock. I want to maintain what I have. I don't want to backslide. I don't want to lose anything. Okay? But I'm not really trying to take it in a new direction. Right? That's one way to think about this. If that's how you're thinking about it, and you get a starter flock of 4 dozen chickens, you just split them into 3 groups, and those are your families. Okay? Put leg bands on them, split them into 3 groups, you're good. Okay? If you apply it that way, and that's all you do, it is a very good method for maintaining what is and preventing genetic drift. But you can also take this one step farther. And you can say, what I have is good, but I want to introduce something. Okay? Or, what I have is good, but I want to emphasize something. Or multiple somethings. Okay? If that's the case, then we're still going to have, most people are going to be thinking 3 or 4 families. You can have as many families as you want. You really need at least 3 for this to be effective and not devolve into line breeding. But if you want to have 15 families, great, go for it. You better have a lot of facilities, but there's nothing preventing you from doing that, okay? But you really don't want to do less than 3, or you're not getting the benefits, and you can, again, kind of devolve into pseudo line breeding. But the way we view this, if we want to make directional change, is that in each of these families, we are going to rigorously select for or against a specific thing. Okay? So let's say you have a breed and it's basically where you want, but it's a little undersized, right? So maybe one family, maybe family 1, these we're going to select for size, vigor, and rapid growth, okay? We're not line breeding. We're not going to try and fix a specific single trait. We're going to select in a direction. So we're going to think of this as the fast growth line. Maybe also we want some more eggs, right? So maybe family 2, we're going to select for egg production, set up trap nests and actually measure, hen's productivity in terms of eggs, okay? And then maybe family 3, we want to select for mild personality or something else, whatever you like, right? Just to run an example. So here we will select the most mild-mannered chickens, okay? Now, again, that's under hormonal control, like we were talking about before. If you can select for cockfighting chickens, you can select for, happy, peaceful chickens. It's a thing. It's all just testosterone level. Anyway, in each of these families, we're selecting for that one trait. So in family 1, we will tolerate a hen that doesn't lay as well, as long as it grows fast. In family 2, we will tolerate a hen that doesn't grow as fast, as long as she lays well. Okay? In family 3, we will tolerate the runts that don't lay well, as long as they have great personalities. Okay? So in each of these groups of chicken, you're selecting for something specific. Okay? Also notice my numbers, right? I'm setting these up with a dozen females and 4 males. That's a really good ratio for effective population, right? This hypothetical starter flock has an actual population of 48 and an effective population of 36 up here, okay? So we haven't lost much effective population. If you do this one rooster each and you do the same thing, you're going to crash your effective population very quickly, and now we're back to inbreeding done by accident and badly. Mm-hmm. Okay? Don't do that. Don't do that. You have to have enough males to maintain a good effective population. Okay? And yes, in this example, that does mean a dozen roosters. Now, the next step, we've set it up, right? We've decided how we're going to define them. We breed. Okay? So each of these groups is going to produce an F1 generation. This F1 generation is where we're really starting to apply this selection. Okay? If this is a starter flock, we probably didn't really know that much about their history, how fast they grew. You could already select on personality. You could already select for egg production, right? We probably can't select for this one at all. But we will do the best we can, right? We might monitor egg production for a couple of weeks and just pull the best into here. And monitor behavior and pull the best into here, and then the leftovers are there or something. You know what I mean? So first generation, you're getting what you can find. Mm-hmm. And again, we live in a world which has had a lot of line breeding done wrong. So sometimes what we can find ain't great, right? But you got to start somewhere. You got to start with what you can find. If you can talk to individual breeders who have had high quality breeding programs, either something like this or line breeding with test crosses, and you can get those stock, well, then you might know a lot more about their history and could sort these out better. Mm-hmm. But if you don't know that, you don't know that. So you sort them out as best you can. Now, in these offspring populations, here, right, we're going to really pick for the fast growers. Okay? Here, we're going to really pick for the good layers. Here, we're really going to pick for the friendly. Okay? And you are going to save some males and some females. The females stay in their family. Okay? This is how we're going to apply consistent selection within this group. Mm-hmm. Okay? If we selected the F1 and then moved all of them somewhere else, we would lose the ability to have a consistent directional change in this family. Mm-hmm. But since we're going to take all of the females, and we do have a female-dominated population, this will gradually move in the direction of fast growth or large size. Okay? Here, same with eggs. Here, same with personality, right? But the males move on to the next family. Okay? So all males born to family 1 will be introduced into family 2. Okay? Likewise, we get our offspring, we select them for eggs. All of these good egging females stay in family 2 because that's where we're really applying selection for that trait. The males move on to family 3. The nicest, friendliest families to family 3 stay in family 3 because these are our, good neighbor next door chickens, right? But these friendly males are going back over to family 1. So it's a compromise between selection and directional change within a group with the distribution of those traits across the larger population. Okay. This allows us to work with more than one traits at a time. You can still really only work with one trait at a time, but we have multiple families, right? Here we're working with one trait. Here we're working with one trait. Here we're working with one trait. If you want to work with 5 traits, you need 5 families. That's going to take a lot longer to make the progress you want to make, right? 3 families, 3 traits. Don't work with more than one trait at once. Okay? So you have to pick and choose. What are you going to emphasize? What are you going to tolerate? Okay? This and disease resistance are actually what I am least willing to tolerate, right? I demand that my animals are friendly, and I demand that my animals are hardy, first and foremost, right? Everything else follows that. Then production traits, and then, if I get around to it, maybe I'll care a little bit about what the breed standard says about foot color. But I really don't care, okay? Because it's irrelevant, basically. So let silly, irrelevant things be silly and irrelevant. You don't want to emphasize foot color in one of your families. If you're saving 5 chickens and you need a tiebreaker between 2, sure, maybe you can think about it. But that's as much brain cell as I will give that. 1/2 of one brain cell occasionally. But personality, you cannot have animals that are going to try and beat you up. You cannot do it. You just cannot do it. And you cannot have animals that are going to need constant veterinary intervention. You must have hardy animals. Those are the first 2. Everything else follows after that. So we get the benefit of being able to work with multiple traits in the overall program. Okay? We get the benefit of being able to work directly with those traits and have a strong selective pressure toward where we want our critters to go. Okay? We get the benefit of this movement, right? This gene flow through the population. We're making progress here, and then we're sharing that progress with the next family. Okay? So as this evolves, you will see directional movement in all of those traits spread across all of the families, right? We're not going to have mean fighting chickens over here because we're bringing these gentle males in, okay? So these will change in temperament slower than these, but they will still change in temperament, right? These will change in growth rate slower than family 1, but they will still change in growth rate. Okay? And doing it this way, and this forced gene flow, right? Structured forced gene flow has the added benefit of working to maintain your starting heterozygosity, whatever it was, for the longest period of time, while still allowing some selection. Okay? That is what this does really well. Now, you still have to have a large base population, right? You can't take 3 trios and call them 3 families, right? Trio being, like trios of chickens is like a male and 2 females. That's not a family, right? 5 trios combined is 1 family, right? You still need a population. You can't do this with a hugely reduced, infinitesimally small population. You need unrelatedness in your starting population, or this is false. Okay? Mm-hmm. See your earlier video for the description of effective population. And it's a compromise between what we can get out of line breeding and what we can get out of random breeding. Okay? It's a really good compromise. The last thing I'm going to say as a plus for this is it makes it really easy to introduce a new trait. Right? Remember I was talking about a hypothetical where you have a flock of chickens and some really cool trait pops up and you line breed for 2 or 3 generations to fix it. Well, you could take some of those females and pop them into all 3 of these families. Or that could be a 4th family. Okay? So this gives you a structured way, right? Let's say I have temperament, eggs, size, and I get some just magically beautiful feather pattern. Well, bam, family 4, right? So those test cross successful F4 or F5 line bred chickens, they could be family 4. Okay? And now we're going to force that really cool gene that we fixed over there into the larger population. And the fact that the larger population is forcing heterozygosity into our line-bred population will undo the damage of irrationally small heterozygosity in that population. Okay? So this is where these methods can fit together and do really wonderful things as an ensemble that you would not see if you're only looking at them in isolation of each other. Okay? So this, clan mating, if you are a hobby farmer, new to agriculture, something like that, this is where I would start thinking about. It's sort of the optimum compromise between all of the extremes. Okay? Mm-hmm. You can still take the results of this and line breed for something specific if you really need to and want to later on. And you could still take this, the results of this, and throw it into a mob breeding program if you really like your final result later on. And that is where we're going to go next. Let's talk about mob breeding. For our third and final breeding technique, this is the least intensive, the most naturalistic of them all. Mob breeding or random breeding. Mob breeding is fairly descriptive, right? You're taking your animals, you're turning them out into a mob, you're letting them do what they do, right? The hens are going to do their hen things, the roosters are going to do their rooster things. Eggs are going to happen, or calves or foals are going to happen, right? Depending on what critters we're talking about. Now, this is a really interesting one. It has a lot of proponents, has a lot of detractors. Like everything, it has some pluses and minuses, right? The plus, it's really good at preserving what exists, okay? When you're doing this type of breeding, it's sometimes called random breeding, but it's really not random, okay? You have 2 selective pressures. First, the farmer. When you're doing this type of breeding, you're not trying to choose the best animals to breed. But you are choosing the worst animals to eat. Okay? So you're not trying to pick the top 10% to become the next family in your spiral mating system. You're trying to choose the bottom 20% to sell at market or eat as soup. Okay? So you're trimming from the bottom instead of trying to choose the top. The animals themselves will choose the top. They will compete. The males will compete, the females will compete for space and food and energy and breeding rights, right? And it will be the most vigorous, thrifty animals that do the majority of the breeding. Okay? So the middle is going to kind of get left out of this equation, right? The bottom just goes to soup. The top gets the majority of the breeding rights. The middle is kind of left out, right? This works in many things. So I'm going to talk about these two examples where this has sort of happened kind of naturally. These are kind of naturally only, right? These are human-caused events. The Chillingham Park White Park cattle. Okay, there are several White Park cattle breeds. They were used by the upper crust of British society as ornamental cows in their hunting parks. And there are still these little fragment herds around. One of them is the Chillingham herd. Okay, the Chillingham herd was established 300 years ago and has not been touched by human hands since then.
They're pretty.
They're really pretty cows. Yeah, they are. And they have a really interesting herd structure, which they are not all that closely related to the wild Uruk. Not any more closely than any other domestic cattle anyway. Okay? But because they have been left to their own auspices, just as a breeding mob, with no human direction for 300 years, they have redeveloped a pseudo-natural herd structure. Okay? And what we see when they've been studied is that there's usually one or a very small number of, they'll call them king bulls, which will basically breed all of the cows for 2 years. Okay? And they really only get a 2-year reign as the king bull. Before that, they're too small and they can't outcompete the king bull. After that, they're starting to decline in health and a younger bull will replace them. Okay? So you have a small number of animals doing all of the breeding, but the selection for those is a very natural, organic. It's the strongest bull. He can fight all the others. He gets the cows. Okay. We've seen in personal experience, we've seen similar things with our free-range chickens. There's one chicken that's a phoenix rooster. His name is Yazgir because he's really, really extra. And when we just take eggs out of the coop and hatch them, I'd say, about 3/4? About 3/4 look a whole lot like Yazgir, right? He's kind of the king rooster. He just runs all over. We've had multiple coops. He just gets into all of the coops because he's a good flyer and does rooster things. So
he fits his name well.
Yes, he fits his name very well. So, right, Yazgir kind of is doing the same thing. He's just the most successful of all of the roosters. We get chicks that look like all of the other roosters, but a plurality are Yazgirs, right? Mm-hmm. Very, very clearly so. So that's what happens, right? We didn't choose to mate this one rooster to all of the others. He's just the most successful at mating. The most vigorous, the most active, the best flyer, the best at getting around and busting his way into all of the coops and breeding all of the hens, whether we want him to or not. So, that's what you get, what you're trying to get in a mob breeding scenario. The selection for the top animal is just the natural success of the top animal. Okay? You're only selecting the bottom out. Mm-hmm. And in selecting the bottom out, you are exerting some pressure toward the future characteristics of the herd by diluting and removing any traits which are deleterious to the animal's health, and you can observe that, or are contrary to what you want the animals to be. Okay? But by and large, it reduces genetic drift and preserves what exists. This is where people will criticize it. They'll say, well, you can't make any genetic gains with that system. It's like, yes, that's the point. You do mob breeding when you already have what you want. Mm-hmm. Okay? If you want to take an animal and turn it into a breed with fundamentally different characteristics, this ain't the way to do it. Right? You use the other things to do it, or you use an outcross to do it. You don't use mob breeding to do that. You use mob breeding to maintain what is. Okay? And it's very effective at that. So these two examples, I already mentioned this one, deliberately placed by humans in a park and then ignored for 300 years. The St. Kilda Island chain is an island chain in the northwest of Scotland, and it was occupied up until about I'm not sure the exact date, like interwar World War II era. It was cleared out. I think it was cleared out for World War II because it was turned into a naval base or something like that. I don't know the details of the human side of the story, but it was abandoned in the early 1900s. Okay, when it was abandoned, all of the sheep just went feral, and that feral life has persisted. Right, they have been selected by the fact that they're feral for natural ability to shed wool. So they shed their own wool. They don't need sheared. And they're just occupying the islands. So these islands are now just big mobs, breeding mobs of these originally domestic sheep. Mm-hmm. And these are two very highly studied populations. I'm going to put down in the video description a bunch of article titles where you can go and read some of the scientific research on the genetics of these two different mobs, cattle and sheep. And one of the things that's interesting about them kind of shows the potential longevity of this sort of program if you are willing to accept a few negatives. Okay? And they're big negatives. But the Chillingham White Park cattle, when we studied its genetics, it was originally hypothesized that this was sort of a throwback to the Uruk, the wild ancestor of cattle. And then when we got good genetic techniques on it, Darwin himself wrote about this population of cattle and thought that, right? It's that old, right? It's that old. But when we got good genetic techniques and we tested them, they're not. That's a disproven hypothesis, okay? They're not a last remnant of the Uruk. They are domestic cattle that a landowner thought was pretty and put there. From their measured genetic diversity, they are extraordinarily purebred for almost everything. Even more than most line-bred lines.
Interesting.
Okay. And they've existed here for 300 years and they're still a strong herd. But there's a caveat. Every couple decades, the population crashes to almost nothing. Okay. Their current population is like in the 40s and 50s. It has been up to 100, 150 at some points in history. When this population crashes, they crash to 5 or 6.
Holy moly.
And then rebreed from there. Okay?
That's a bottleneck.
Yes, exactly. That's why their genetic diversity is so low.
Okay.
Because of the frequent occurrences of bottlenecking. Same thing with the St. Kilda Soay sheep. Yes, there's hundreds of sheep on these islands, but every so often, the population crashes by 75% or so. So 2/3 to 3/4 of these sheep die off. Okay? And then you have this greatly reduced population, and then they build back up, and then they die off again, and then they build back up, and then they die off again. Okay? So what's going on with this? We have, neither of these populations meets the 5,500 rule. Now, thankfully, these are not the only cattle and not the only sheep. If these were the only cattle and the only sheep, we would not call them viable populations. We would say these species are going to go extinct eventually. Okay? These breeds won't go extinct eventually because humans have them, and humans will do enough, at least if they're smart, will do enough outcrossing to rebuild the genetic viability of them for the long term and keep those, basic forms alive. But they do require outcrossing. What's going on? As they breed in this reduced genetic environment, okay, first off, the selection pressure against the weak is mitigating the effects of the inbreeding depression, right? Since only the strongest bull can become the king bull, right? The ones with the most inbreeding depression never get to be king bull. So that moderates the effect of the inbreeding depression. Okay? And then when we have those population crashes, the most purebred individuals are the ones that are dying. Okay? So the ones with the more heterozygosity are more adaptable, have stronger immune systems. So they're the ones that are surviving the crashes. But it's bottlenecked, it's severely bottlenecked. It doesn't have 5,500 rule behind it to begin with. So they then, breed out, that inbreeding depression accumulates again until you have another catastrophic crash. This is particularly evident in the Soay sheep. And their pattern is, they're on an island, so they have a restricted food source. So part of it is they start to weaken because they don't have enough graze. They don't have enough pasture. And as they start to weaken, the parasite load increases. As the parasite load increases, it kills all of the sheep with weak immune systems. The most purebred. Okay, so it's resetting heterozygosity back to before the pure breeding occurred. So I have a big problem with some breeders who say mob breeding works because of these. Well, mob breeding works, but if you want to emulate this, you've got to accept a 75% loss in your cattle herd every 10 years. You're going to go bankrupt if you do that, right? You can't do it this way, okay? But mob breeding still works, because what we can do as thinking humans exerting some control over the situation is we can allow the benefit of competition between males to select for the best. And then when we select the worst, we're selecting out those that are too purebred. Right? We're selecting those out manually and never allowing the population to grow to the point that those excessively purebred bad animals become a plurality of the population. Okay? So we're using a little bit of intelligence to head off that problem. And that's why the combination of allowing nature to pick the best and humans to pick the worst is a very, very good compromise between the natural impact of inbreeding on a population and the human need to have a stable population in order to manage a farm. Okay. I do think this method has a lot of benefits. Its main downside is it takes a lot of land. Okay. And again, I'm trying to target these as small farms. You can do this with chickens even in a small farm. Right? You can absolutely do this with chickens in a very small area. You can do this with sheep on 20 or 30 acres. Okay? But if you want to do this with horses or with cattle or with something really big, you need a large broad acre farm. Okay? You just need the pasture space to have the animals. This is not a method that you can do with just 3 or 4 dozen animals. Okay, you can do spiral breeding with just 3 or 4 dozen animals. You cannot do mob breeding with just 3 or 4 dozen animals. You need, more like 75, 100, 150 animals. You need a population size to have enough competition to successfully pick the best and enough observations for you to successfully pick the worst. Okay. So don't try to do this unless you're really committed to a truly large population size, because you don't want to be the Chillingham population on your farm, right? You don't want to be this. It's a fascinating scientific case study, but it's bad agriculture, So keep these things in perspective. Right, and keep that in mind when you hear stories about this marvelous, magical Chillingham White Park cattle population. They're not magical or marvelous. They're naturally culled in ways that are not tolerable on a farm. I hope this gives you some food for thought and puts these methods into perspective. If it has, I would be ever so grateful if you gave the video a thumbs up. It helps me know that I'm helping you, and it helps the YouTube algorithm know that you enjoyed it, and it will push the video out and show it to others. So I'm always most grateful when you do that. Now, this set of methods is certainly not all there is to breeding. right? We're looking at methods where we're assuming you have a population that you want to work with. But there's also times where you have a population that you want to change, sometimes even change to a large degree. That's where outcrossing comes in. Okay? You can also have a population that has accrued so many deleterious traits and conditions and excessive pure breeding, not enough heterozygosity, from bad application of some of these methods that it needs a rescue. That's also where outcrossing comes in. And that's going to be the fourth video in this series, how to think about when to apply and the effects of outcrossing as a mating technique. So, I hope that you will join us there, and I'll see you next time at Old Ways Rising Farm.